is first shifting theorem. We are now seeing first shifting theorem in Laplace transform. First shifting theorem or first shifting property. We know L of f of t equal to e power minus t f of t dt. The S is we are integrating with respect to t. S is other than t. Result will be function of s. Its result will be function of s. L of f t function of s. Its result will be function of s. E power a t f of t. 0 to infinity. E power a t. E power minus s t. F of t dt equal to 0 to infinity e power minus st e power a t f of t dt equal to 0 to infinity e power minus st plus a t f of t dt equal to 0 to infinity e power minus of s minus a t f of t dt. I am writing here. We are integrating with respect to t only. If you integrate, the result will be function of s minus s, since s minus a is other than t. Therefore, this is function of s minus a. See, theta of f of t is function of s. Similarly, this is for s minus a other than t, therefore function of s minus a is the result. Therefore, it can be written as phi of s changed into s minus a equal to phi of s is L of f of t. L of f of t equal to bracket s to s minus a, s changed into s minus a. This is the proof for the first shifting theorem. See, we have seen L of e power a t f of t equal to L of f of t s changed into s minus a. Similarly, L of e power minus a t f of t equal to L of f of t s changes into s plus a. Here positive comes negative. Negative means positive. This is called first shifting theorem in Laplace transform. Initially we have seen many sums by applying this initial value theorem. Applying this first shifting property, I wrongly mentioned. This is first shifting property. Differentiation in Laplace transform. L of f of t theorem. L of f of t equal to 0 to infinity e power minus st f of t dt. Its result is function of s equal to function of s. Let us write here function of s. L of f of t equal to function of s. Instead of L of f of t, we are writing function of s equal to 0 to infinity e power minus st f of t dt. Differentiating both sides with respect to s, d by ds of phi of s equal to d by ds of 0 to infinity e power minus st f of t dt. This is function of s. Laplace transform is function of s. L of f of t equal to function of x. We are differentiating with respect to s, d by ds. Similarly, we are differentiating right side also differentiation with respect to s. S here only comes. No other places s comes. Therefore, this is the method of differentiation under integral sign. This is the way of integrating differentiation is differentiation under the integral sign. It enters into the integral equal to 0 to infinity d by ds of e power minus st f of t dt. Let us differentiate with respect to s only. Therefore, e power minus st into minus t differentiated f of t dt. Y equal to e power ax. Simple differentiation. dy by dx equal to e power ax into a. Similarly, we are differentiating with respect to s. T is other than s. Therefore, minus t into like a here. This negative comes out minus 0 to infinity e power minus st t f of t dt. Again, minus, its meaning is Laplace transform of tf of t. Tf of t. Left side is d by ds of phi of s. This now becomes this side minus d by ds of phi of s equal to L of t f of t is the result minus d by ds of phi of s is Laplace transform of f of t. Phi of s is Laplace transform f of t equal to L of t f of t. We are writing negative s minus 1 power 1 d by ds of L of f of t equal to L of t f of t we are writing front and back. L of f of t is minus 1 power 1 d by ds of L of f of t. If you remove t, differentiation comes. This is called differentiation in the Laplace transform. Similarly, this is the first step for single time differentiation. Similarly, we can do double differentiation. We know L of f of t equal to 0 to infinity e power minus st f of t dt. This is nothing but phi of s equal to 0 to infinity e power minus st f of t dt. We are differentiating double times d square by ds square phi of s. D square by d square 0 to infinity e power minus st f of t dt. See, we are seeing differentiation under integral sign. This differentiation, double time differentiation, which enter into here only. Here only we are differentiating with respect to s only. Therefore, it will enter to differentiate for this only. Therefore, 0 to infinity d square by d square e power minus st f of t dt. 0 to infinity, let us differentiate one time. D by ds of e power minus st into minus t f of t dt. One time differentiated. Again differentiating second time. Double derivative equal to again 0 to infinity e power minus st. Already t is there. One more t. One more minus t. Cost of s is minus t. We are differentiating with respect to s. Therefore, minus t again comes. F of t dt equal to 0 to infinity e power minus st t square f of t dt. Left side is d square by ds square phi of s equal to 0 to infinity e power minus st t square f of t dt. This is nothing but Laplace transform of t square f of t. See, negative double time comes. Therefore, this we are writing here minus 1 whole square d square by d square phi of s minus 1 whole square d square by d square phi of s is L of f of t equal to L of t square f of t. See, finally we are writing L of t square f of t equal to minus 1 whole square, which is positive. We are writing like this, L of d square by ds square L of f of t. This is double time we have differentiated. Similarly, we can prove L of t cubed f of t equal to minus 1 whole cubed d cubed by ds cubed L of f of t and so on. Generally, we can write L of t f of t equal to minus 1 power 1 L of d by ds of L of f of t. One time differentiating L of t square f of t equal to minus 1 whole square d square by d square L of f of t. Similarly, L of t cubed f of t equal to minus 1 whole cubed d cubed ds cubed L of f of t and so on. Generally, L of t power n f of t equal to minus 1 whole power n d n time differentiating ds n L of f of t is the proof, is the differentiation in Laplace transform. Again, we are going to see integration in Laplace transform. This is also a theorem. we are going to see integration in Laplace transform. L of f of t equal to 0 to infinity e power minus st f of t dt. L of f is function of s. T is s is other than t. Therefore, this will be function of s. L of f of t equal to function of s. This is function of s equal to 0 to infinity e power minus st f of t dt. Integrating on both sides, integrating on both sides with respect to s from s to infinity. Therefore, s to infinity phi of s ds equal to s to infinity 0 to infinity e power minus st f of t 0 to infinity in bracket e power minus st f of t dt ds. If integrate with respect to s means ds would come, here also ds. See, we are integrating with respect to s only. With respect to s only. Therefore, this integral belongs to for s only. For s only. Therefore, it will enter into here only for this exponential. Here is s. Therefore, it will enter into for exponential power only. Equal to 0 to infinity. It comes inside s to infinity e power minus st ds of f of t dt. This ds comes here and this integral also comes here. We are integrating with respect to s only. Equal to 0 to infinity integrating e power minus st by minus t. We integrate with respect to s only, but minus t is quotient of s. Therefore, it comes down f of t dt. Integration of e power ax dx equal to e power ax by a. Instead of a, here minus t comes. Limit is s to infinity. We are giving limit inner side. You are giving upper limit for s only. S is infinity. E power minus infinity comes, which is 0. 0 by minus t, 0. Again, lower limit s. Instead of s, the same we are giving. Minus st by minus t. Instead of s, we are giving same s in numerator. F of t dt equal to 0 to infinity, negative positive. Therefore, e power minus st f of t by t dt. It is nothing but Laplace transform of f of t by t. Therefore, left side is s to infinity phi of s ds equal to Laplace transform of f of t by t. This is nothing but phi of s is L of f of t. Therefore, s to infinity L of f of t into phi of ds L of f of t by t. Again, we are writing the same, again equal to s to infinity L of f of t ds. We have seen already many sums in this. If t removes, integral comes at the right side. Therefore, this is the proof for the, if you remove one integral, similarly we can remove two integrals also. Same, L of f of t is function of s. Function of s equal to 0 to infinity e power minus st f of t dt. Integrating both sides with respect to s double time. S to infinity phi of s ds ds. S to infinity 0 to infinity e power minus st f of t dt, outside ds double time ds s to infinity double time is 0 to infinity. This is, see, right side we are integrating with respect to s only. S here only comes. Therefore, do both integrals enter into this 0 to infinity in bracket s to infinity e power minus st ds outside f of t dt. It comes also, f of dt comes outside, these days entering e power minus, double integral also entering into this. 0 to infinity s to infinity, one time integration is e power minus st by minus t. One time integrated ds is there, s to infinity in bracket f of t dt. Again, giving limit 0 to infinity s to infinity, giving upper limit e power minus infinity by minus t, lower limit e power 0 by minus t ds in bracket f of t dt. 0 to infinity in bracket s to infinity e power minus infinity is 0, e power 0 is 1, therefore 1 by t ds double time integrating, we are double time integrating. First time integrating is e power minus st, e power 0 not comes, limit is s to infinity. Give upper limit infinity e power minus infinity by minus t, lower limit is in s is the same as minus t equal to e power minus infinity upper limit, which is 0 plus e power minus st by t, one more ds is there, ds f of t dt, one more ds in bracket f of t dt equal to 0 to infinity s to infinity, again e power minus st ds, this t goes out, f of t by t dt. We are integrating just s only. Again integrating 0 to infinity e power minus st by minus t, limit is s to infinity f of t by t dt equal to 0 to infinity limit, upper limit e power minus is 0, lower limit is e power the same as s by minus t f of t by t dt 0 to infinity e power minus st minus plus plus f of t by t square dt. This is nothing but Laplace transform of f of t by t square. Left side is s to infinity phi of s ds s to infinity phi of s is L of f of t L of f of t by t square. Phi of s is phi of ds we have to write ds L of f of t by t square. Again, writing front and back, L of f of t by t square equal to s to infinity L of f of t ds. Similarly, we can prove L of f of t by t cubed equal to s to infinity triple time s to infinity L of f of t ds. In general, L of f of t by t equal to s to infinity L of f of t ds. L of f of t by t square equal to s to infinity L of f of t ds. See, one time if remove t, one integral t square double integral. Similarly, t cubed L of f of t by t cubed equal to s to infinity L of f of t ds. Triple time. Similarly, we can prove any power for t in the denominator, but t and t square only possible. T cubed is very biggest one. Simply, it is not possible to do sums.